Hello, dear students and friends. Welcome to Billion Hope. This is Sandeep Manudhane, your mentor Sandy, bringing you AI for real impact. Today, we are in session number 3 of the series of 7 in our Masterclass playlist, AI for Everyone. Irrespective of who you are, a beginner, a non tech professional, a strategist, a corporate professional, you can learn AI. And this is what the playlist is all about. So, this is our session number 3. Make sure that you have already studied and watched session number 2 and 1. If not, do it today. So, what's the topic for today? A wonderful topic, the foundations of machine learning. We keep hearing about the term machine learning every single day. What exactly is this thing? How do machines learn, if at all they learn? We are going to demystify this supposedly complex topic. And in a few minutes from now, you will say, oh, it was so easy. I wish I would have learned it earlier. Well, now you have. So, welcome once again to Billion Hopes Under the Hood Foundations of Machine Learning. This is my masterclass playlist, AI for Everyone. I'll be doing 7 sessions in this. Other sessions on YouTube are being constantly uploaded. Keep learning. Enjoy. This project, Billion Hopes, is my baby, designed for beginners, non tech professionals, and strategists. We are in an AI first era now. AI is completely upon us. We cannot escape it. So it's best that we learn it, we begin deploying it in our lives as well as in our enterprises to increase our productivity and to make the most of whatever good AI has to offer. Have you subscribed to a free newsletter yet? If not, you're missing something. Every Tuesday and Friday, the new issues are sent. Wonderful compilation of AI facts, wisdom, and learning right in your mailbox. Go ahead and fill the form. The link is given in the comment. Do not miss this at all. And make sure that you visit the current affairs of AI site Insights every day, full of hundreds of beautiful posts. So, as I said, we are on session number 3. My very first session in this masterclass playlist was all about a general orientation to AI. People loved it. Thank you so much. And we got so many suggestions. Thank you. Keep them flowing. Keep commenting. Keep telling us what good you are seeing here and what we can improve upon. We have also started the testimonial link. It's given in the comments. It would be lovely if you appreciate our work and fill a small testimonial. It will feature on our site. Thank you, thank you, thank you. Today's session number 3, machine learning. The next session would be AI's creative engine. Session 5 would be how AI is impacting jobs and workspaces across the world. 6th would be how do you strategically use AI to win? And finally, 7th would be super intelligence. Is AGI arriving? Where are we headed over the next 10 or 20 or 30 years? That would be session 7. So this masterclass playlist will be a masterpiece. With your love and support, please keep sharing and taking it to all your friends. Session number 3 is now on. So if somebody asks you, tell me a roadmap to begin learning machine learning, ML concepts and all, perhaps a reasonably good roadmap would be something like this. Machine learning being a very vast topic, you could start with foundations and data. Then you could cover the types of learning and the paradigms of learning. I'll give you a hint on each today. Then you could get into the details of the process of machine learning. Then the core algorithms and models, which is the toolbox. Then the key challenges and concepts. And finally, applications and the future. This is a reasonably good roadmap for any person willing to start learning ML. And what is the overall time that person would need to learn ML in totality? If you're starting from zero and you have a maths background, then maybe 2 to 2.5 years. If you do not have a maths background at all, then maybe you'll need to spend a couple of years learning basics of maths, which are used in machine learning. You have probability, you have statistics, you have algebra, you have linear algebra, you have calculus, you have geometry. That's it, nothing more. That's it, nothing more. Yeah. What to do now? That's the fundamental thing. But Billion Hopes actually brings AI to people, removing all these technicalities. So at least on the application side, you can make the most of it. Of course, the technical side, which is the ML ops or the DevOps side, that's a different ballgame altogether. So fine, let's focus on the non-technical issues and learn as much as we can and stay smart and ahead in the race. Recall the first 2 sessions. We have already started. Recall the first 2 sessions. I had shared this beautiful AI taxonomy with you. Taxonomy refers to overall classification or nomenclature system. So AI is a very vast field, and anyone who says that I am an expert in entire artificial intelligence, well, that's like saying I'm an expert in entire medical science. It's a fallacy. It cannot happen. It's a fraud. So AI taxonomy tells us that AI is a vast field. And today, my area of concern is machine learning. This beautiful sky blue box here. I'm going to focus on machine learning, which actually is the bulk of AI application we see in the world. Now, a question is bubbling in your mind. Can you show me how machine learning is actually used? I mean, I don't see it anywhere. I don't see any machine working as such on its own. So, can you show me how machines actually work? Wait a minute, I'll show you multiple applications. And I'll also tell you how it happens under the hood. That's our title for today, right? So, we are focusing on this entire region today, machine learning. And even if you know nothing, if you can just be with me till the end, you will know everything about it at a basic level at least. Where do we really use ML? In the real world, do we even have any use of ML? Okay, show me some example. Yes, sir. Your wish is my command. Here we go. These are just 7 applications of machine learning. I could bring up 70 right away. So, what are these applications? Well, my dear friends, machine learning is embedded into our lives like nothing else. Medical imaging, tumor detection. When machines do the scanning, of course, humans can do it wonderfully well, and machines learn from humans only. They have detected this machine learning algorithm, for example, detects a lesion, which could be a cancerous lesion, tumor, and it gives a confidence range. So here it was 98%, right? And powered by ML. So this is convolutional neural networks for segmentation, as you can see very, very clearly. Any doubts about it? So that was a convolutional neural network for segmentation. We are talking about this part. Is that clear? Now we come to the second one, finance, stock market predictions. Of course, this is not at all reliable, but a trend prediction can happen. LSTM, long short term memory networks, have been used to some extent successfully in doing sequential data prediction. Third, e commerce recommendations. So, all the carousels you see of recommendations are basically completely machine learning powered. Netflix recommendations, or YouTube recommendations, or Amazon online commerce recommendations. Recommendation engines have boosted the incomes of these platforms because it makes you stick to that place and buy more over a period of time. So, recommendation engines, which actually absorb your behavior and accordingly start presenting versions of reality to you, is or recommendations engines are one of the most successful commercial applications of machine learning. That's why most companies, they love investing in recommendation engines. So this is a beautiful real world hard application of machine learning, manufacturing, robotics and quality assurance. And the kind of machine learning you use here is computer vision. So instead of a human being looking at millions of products coming out, a computer vision empowered or powered machine learning apparatus or system or algorithm can almost do 99% of the job beautifully. So this is actually deployed at scale across the world. Agriculture, drone crop analysis. So this is a machine learning system. You first train it. Now I know the question in your mind is, how does the drone know what kind of a cropping has happened and what crop is failing and what? Of course, somebody would have trained the machine learning system inside that physical body of the drone. So that training process is the real question. How do machines actually learn? We are going to see that in a moment. So this is remote sensing AI, the drones, education. Tremendous use of machine learning here because you can do hyper personalization and you can actually do a lot of knowledge tracing. So machine learning systems, by virtue of their being AI, not having any soul or any human fallibility in terms of losing patience, The AI systems and machine learning systems will be infinitely patient with any learner, thereby making it easier for the learners to gel with them. Of course, the downside of this is agreeability. If the systems are too agreeable or too sycophantic, then the learner may end up getting a very wrong notion of her abilities. All these are basically huge hot topics, raging debates across the world. AI and ML is evolving, right? Go ahead and tell me in comments what are the risks from AI. Love hearing from you always, love listening to you. And smart city and traffic optimization. The whole idea of a completely smart city is integrated operations, right? And that's not possible without machine learning. So I just showed you barely 7 examples of machine learning. There could be 70 more right now. This is why we cannot run away from machine learning. So let's dive deep into machine learning and learn it. So now you are telling me you are a 10-year-old, and can you explain machine learning to me? As I said, your wish is my command. Let's learn machine learning from the perspective of a 10-year-old. So this is a 10-year-old. And this lovely child of 10-year-old, there's a child in all of us, right? We should never let that child die. We should always keep that child alive. The best learners are childlike learners. They always start from ground zero, asking good questions. My experience as a learner myself and as a teacher over more than 3 decades now has been always start from ground zero, ask innocent, simple, silly questions, and your learning is perfect. Unfortunately, out of guilt, out of shame, out of embarrassment, out of feeling awkwardness, a sense of awkwardness, people tend to avoid asking questions. One good thing about AI and ML systems is that people can ask any type of silly question and there's no one to judge them on the other side. So maybe that also explains to a great degree why AI and ML systems have caught up with students across the world. Let's see what happens over the 5 years, next 5 years, I don't know. So, how do computers learn like you? When we say computers learn like you, I am actually talking about machine learning systems, right? So, how do computers really learn like you? The very first thing is we give them examples. First, we show that computer, which is a machine learning system, this robot is only a representative. You don't have real robot. These are all invisible softwares working inside the machines. So we first show them lots and lots and lots and lots and lots and lots, and I really mean lots, tens of thousands of images. So the machine slowly starts extracting patterns. How do dogs differ from cats? They slowly start absorbing those patterns. Got it? Then they find patterns and they try answering what is what. Inevitably, they go wrong most of the time. In the first few thousands of epochs of training, they would go wrong. Then, when they go wrong, you actually correct it. Every time they go wrong, you tweak the knob, so to say, and make it understand that, okay, this is where you got wrong. The technical word for this process is you do a forward pass first, then you do a backward propagation pass or a back prop, and you use loss minimization and gradient descent techniques to actually adjust the knobs, basically weights and biases, the parameters across the network. But if you're not using a deep neural network, then you will still do it adjusting of the knobs, figuratively speaking. The more examples the machine sees, the better is the reproducibility of reality. So, the more is the training you do, higher is the confidence level of the machine in answering something. Got it? This is how machine learning systems work. So, that was like a 10-year-old, but many of us here are not 10-year-olds and we want something better. Fine. So, we are getting into that. What's the most basic process in machine learning? I'm coming to that. Before that, in my earlier sessions also, people have shown a lot of interest in learning about how human infants actually learn. And what is the process in human beings? How do we become so generally capable, generally intelligent, which no machine so far has been? That's the holy grail kind of robotics and all. Well, an answer to that could be found in a very simple truth: innate priors in human infants. All of us, when we actually arrive in this world over the many, many millennia of training that we have received as part of our DNA coming from humanity, the innate priors, they exist in us. There are built in capabilities within us, reflexive behaviors. So, these are the various behaviors that infants are capable of without even having learned human language. Infants may have not learned human language, but they already are endowed with many other innate priors. So never judge a human being by the quality of language that he or she can actually converse in. Your command over the language is the very latest skill. The original skill, which has actually kept humanity alive over the millennia, over the centuries, over the eons, in fact, is the innate prior that gets built into us right from birth. Fine. So I just thought I'll touch base with this and let's move on. Our goal is machine learning, not human learning today. So now we ask ourselves the most basic question. What is the core process in machine learning? So we had explained this to our 10-year-old version. Now let us explain it to our mature version. What is the basic process in machine learning? Okay, here is the basic process in machine learning. Step number one, data is collected. Without data, there is no AI, there is no ML. It's all nonsense. Data is converted into features because raw data will have no sense. You have to actually add features to it. I'll soon come to that. And you will have an output label. So features and labels. And once you add feature, data converted into features, the model then starts predicting using the current parameters. Most of the initial learning trials go absolutely kaput. Machine learning starts with a near 100% error rate, and the humans controlling it ensure that the algorithm constantly, iteratively improves the accuracy of the algorithm. Initially, it will start with a near 100% absolute garbage output. That's what machines are supposed to do. They don't know the human world, right? Slowly, the error is minimized. Slowly, backprop happens, and the error rate goes down, and the machines start performing better. Errors are measured, and the model updates itself. This is what I meant. Iterative improvement, reduction of future errors. This is how a machine is made to learn. But then this is very abstract, right? Let's put some image to it. So this is the secret. The secret is the feedback loop. And how many such feedback loops will you do? Tens of thousands at least, maybe hundreds of thousands, depending on the complexity of the real world data we are expecting our machine to handle. Maybe millions. The large LLMs would undergo such a massive range of training, scope of training. That's why you need those huge data centers for training. That's why you need billions of dollars merely for training those LLMs and creating a base model, not even the final super tuned model, the base model itself. That's why foundation models are so difficult for companies to build, and only 2 countries in the world, 3 in fact, now have the lead. Can you tell me in the comments thread which are the top 10 foundation models in the world? Would love to hear from you. Keep the comment thread alive. Make sure you like the session, share it, subscribe to the YouTube channel we have. Your love and support will make it successful. Step 1, make a guess. Step 2, check the answer and compare it to the ground truth. Step 3, learn from the mistake, which is tweaking of the knobs. Step 4, try again. Iterate, iterate, iterate. And that goes on and on and on and on mindlessly. So basically, this is why people who mock ML and AI, who make fun of it, always say pattern matching is not intelligent. Because this is what is pattern matching, right? So pattern matching cannot be called, or curve fitting cannot be called intelligence. So when you hear someone mocking ML and AI using terms like pattern matching or curve fitting, this is what they're actually talking about. Because this is the process of ML. Step 1, make a guess. So the machine, we have done the initial steps. I have not covered that in this chart here, in this beautiful diagram here, of getting the data, turning it to features. All that is done. Now we are on the actual learning part. Make a guess. The machine tries it. Is this a dog? If it says yes, then we know it has made a catastrophic error. Correct answer should have been cat. Error signal is sent. You check what the answer was and what the truth was. Then you learn from the mistake. You adjust the rules. Basically, the weights and the biases, the parameters are updated. This is called the training cycle overall. And you repeat it again. In fact, modern ML systems do it literally hundreds of millions of times. The GPU clusters, the TPU clusters, the modern AI chips make this kind of an iterative training possible, which was not there 20 years ago. So the large scale ML models being built today are being built because the chips are allowing it to happen. Otherwise, it wouldn't have been even possible. Is that clear? So the secret is not magic, it is pure practice. Practice as in a mechanical sense. Of course, it's a machine, so every sense will be mechanical here. Are you with me? Enjoying the session? Enjoying the masterclass playlist? I'm trying to bring complicated knowledge in a simple language to you. I'm trying to simplify these complexification because I feel every person has a right to learn AI. Over the next 5 to 10 years, we are going to be an AI first world, whether the financial bubble of AI bursts or not. Secondary issue. AI is here to stay. It's not going anywhere. Let's all learn it. Let's all begin deploying it in our enterprises. Let's all actually leverage it to the fullest while being mindful of the downsides as well. So, is this clear? Later on in today's lecture, I will touch upon hyperspace. What a wonderful thing. This is not the hyperspace or the wormhole of beautiful movies, beautiful Hollywood science fiction movies. So there you have wormholes which can help you traverse astronomical distances in just a few moments or few hours, which can connect to completely different points in space and time that otherwise linearly you couldn't have. But that hyperspace and those wormholes, those are constructs of science yet to be physically proven. Here we have something which we actually have proven. Yes, I was referring to Interstellar only there. You watched Interstellar, loved the music, loved the idea. So, can you summarize Interstellar in just a few words in the comments? It would be nice. And don't use an LLM to do that. Using an LLM to do that is cognitive offloading. Doesn't work, right? In a little while from now, I will come to this concept of hyperspace. And how do we have 100 or a 200 dimension space working in it? Because our mind cannot see anything beyond 3 dimensions. We are not creatures of 4 dimensions. So we cannot imagine. If any person says, I can imagine 4-dimensional space, well, he truly is imagining things. So my best wishes to him or her. So we'll come to this. I've just introduced the concept of the hyperspace from here. Okay. Right. So let's move one step forward. A common question is, well, okay, I agree. There are so many applications of machine learning. I agree. You start from data, you put the features on it, you give some labels, and you ask it to do it iteratively, and you keep fixing and tweaking the knobs and stuff. And finally, the machine learning model should work. But then my question is, there are so many machine learning algorithms. What are they? What do they do? Why do we need so many? Can we not have a master algorithm? Well, so far we haven't been able to build a single master algorithm. So there are literally hundreds of machine learning algorithms. But like always, some of them have won the race. They are absolutely on top. And we are going to see which are those ML algorithms. Don't worry at all. Even if you are from a completely non-mathematical and non-technical background, you can still understand this. Just be with me till the end. You will be surprised how much you will actually start talking about ML and AI. This beautiful cheat sheet, in fact, from scikit-learn about what machine learning algorithm should you apply when is a masterpiece. I've taken it from scikit-learn. It says that start. If you have more than 50 samples, fine. Otherwise, get more data. Machine learning is not for you. Got it? Less than 50 samples of data in any given use case, machines can't learn. Machines need tons and tons of data. So less than 50, sorry, get 50 or 100 more at the bare minimum. Greater than 50, grades. What is the job? You need to predict a category. Okay. So do you have label data? Okay. More than 100,000, then these are the classification algorithms available. SGD classifier, kernel approximation, SVC ensemble classifiers, K-neighbor classifier, naive Bayes, linear SVC. Over many years, these algorithms have evolved to be very useful. So far, we haven't come into deep learning yet. No neural networks, no generative AI, no deep learning. This is pure machine learning. Very successfully running for many years now, since 1960s, in fact. So, and then if you do not have labeled data, there's a different clustering application that you can have. K means clustering, spectral clustering, GMM, mini batch K means, mean shift, hundreds of options possible. And if you do not want to predict a category, that is, you're not into classification game, then you are into a regression game. At the most fundamental level, you are either classifying or you are doing regression. Whether you need to predict the quantity, then you have these. If you do not, then you have these. So, this is a logical flow of the various algorithms and how you use them. So, this is more at a practitioner level. The reason I showed you this is where the story is building to. So, just relax. You, I'm sure, would not have heard of a single name here. It's perfectly fine. The same was the case with me when I actually started learning AI way back in 2018, seriously. So now we take a step back. We try to connect the dots with lecture 1 and lecture 2. If I ask you from 1940s onwards, can you tell me 10 things, 10 innovations that brought us here in the field of AI? So today you and me on our fancy mobile handset or a regular mobile handset can just create intelligence on the spot using the cloud and the internet. This was unthinkable just 5 years ago. Forget about 10, 15, 20, 30 years ago. People would have laughed if anyone were to predict what's happening today. So, what brought us here? What are the top 10 innovations that brought us here? This is what we need to see now. Well, these are the top 10. Once again, you may not know many of them. Doesn't matter, doesn't matter, doesn't matter. You keep watching all my videos across various playlists, you will learn all this. And still better, come to my academy, join the courses, and get a structured learning into all these things via various courses that might suit various learning needs. The first innovation, which is my focus for today's lecture, Perceptron. Perceptron was motivated by human neurons. You remember Santiago Ramon y Cajal? I showed you the book. The guy who actually sat down for decades in his library, mapping the neurons on slides and drawing it by hand. It's pioneers like these who have brought us here. So we should always recognize their contributions, the absolute OGs. So in the late 50s, another genius thought, why can I not build an artificial neuron, a mechanical neuron called a perceptron? So that's a beautiful name given, perceptron. You will be surprised to know today, in the late 2020s, modern LLMs with their hundreds of thousands of millions of artificial neurons still follow the fundamental architecture of the perceptron invented in 57. Yes, instead of linear activations, now we have non-linear, tens of non-linear activations to capture non-linear patterns in data. But imagine, after 7 or 8 decades, the original idea of perceptron is what is applied to every neuron in today's deep learning neural networks. That's the power of ideas. They stick around. So the first one is perceptron, and we are going to focus on this. But then, since we have opened the Pandora's box, so to say, the 10 big ideas that actually built AI, backprop, CNN, RNN, LSTMs, word embeddings, attention mechanism, transformers, GPT family, diffusion model. All that for later. Let's focus on perceptrons. Got it? So the question again is, how did this field actually get started? What were the original ideas like? No field of human endeavor comes into being overnight. What we see as an overnight success has a long trail of effort going back decades. Nothing could be truer than this for today's LLMs. The kind of contributions that many legends have actually been making for the past 150 years is why we are here today. Everything came together at the right time, so to say. So the question was, how did the field of ML actually get started? What were the original ideas like? Before perceptrons came about, many researchers tried copying the human brain, the human neurons, and they all failed because Mother Nature is still not ready to truly share her secrets. We have mapped the human brain, we have mapped the neurons, we have done slice wise analysis. Till date, right now, we have no idea how the human brain actually learns. What is the algorithm? We have no idea. Nobody knows. Forget the human brain for a small worm like C. elegans, just a few hundred neurons. We have mapped it physically. We know how the anatomy and the physiology and the neuronal structure is. But what is the learning algorithm? We don't know. So we cannot reproduce even that worm. Forget about reproducing human intelligence. What happens 10 years from now, I don't know. But at least this is the situation as on date. Got it? So shall we start with the first steps in machine learning? And perceptron comes immediately thereafter. We are coming to the full story of perceptron. There is no machine learning without perceptron. So we are going to focus on perceptron. Okay, here are the first three steps. Take a look. So here we are. The early steps in machine learning, right? How did the field of ML get started and what the original ideas were like? The very first step was the McCulloch-Pitts neuron, 1943. It was a logical model, but it could not learn. Weights are fixed, not adjustable. So, you are actually laying the groundwork for the future of machine learning. In every human endeavor, this is a repeated story. There are initial groundbreaking innovations, small innovations here and there, and they might fail. Seemingly, they do not achieve some grand success. But that idea is carried on, refined a bit, and then it matures over many, many years or decades. And then we have the LLMs of today, intelligence in our hands. So this was the first McCulloch-Pitts neuron, 1943. Then came the concept of Hebbian learning. Neurons that fire together wire together because neuronal firing is considered to be one of the pathways to human learning. And the key characteristic here was the learning principle for synaptic plasticity, but it wasn't a functional working machine. So the idea was that the experts seem to have cracked the fact that neurons that fire together tend to link together for a long, long time. And so maybe within an LLM today, we could see Hebbian learning traces as well. So these are persistent ideas. And the early control system, cybernetics, very, very important field of study. Cybernetics in living organisms as well as in machines. It's an entire field of study. And feedback loops. So cybernetics showed adaptive behavior and homeostasis, but it was specific to the system and not general purpose at all. So these three were the absolute original thoughts in the field of machine learning. And thinkers and researchers actually built upon these to take it to the next level. I request you to please subscribe to our channel, like and share these videos. Our membership will be opening in a couple of days. Beautiful tiers and wonderful learning resources will be available also right here on YouTube. Hope to have you join our membership on this channel very soon. Thank you so much for your continued support. Now comes the innovation that finally changed everything, the perceptron. And what exactly was the perceptron? And what happened in the perceptron? Well, here's the perceptron. The first machine that learned how to learn. Learning how to learn is a very important phrase. Learning how to learn. Because that's where recursive improvement happens, right? Learning how to learn. So the first machine that learned how to learn, where did the idea come from? Biological inspiration. how exactly do the human neurons connect and communicate through signal? Lot of research happening on it. So the inspired machine learning specialists, they tried building a machine called Perceptron, which was actually, I'll give you the full story. This gentleman here is Frank Rosenblatt at the Cornell Aeronautical University. You would be surprised to see the multi-dimensional, multi-domain contribution of people who actually made machine learning possible. So this was the Perceptron. In the Perceptron, if you had sensors, which are photocells, which actually see an image, for example, you had physical weights and knobs that you could control. These are all analog potentiometers and knobs, something that we studied in school, and summation and threshold unit. And you will have a light bulb, light up or not, yes or no. So this is a physical machine with custom hardware. Sensors have been connected to a decision-making unit. For the first time, something like this has happened. In our LLMs of today, we have millions of neurons, which are just arithmetic, or rather mathematical entities. They are not physical entities. It wouldn't be possible to construct them otherwise. The breakthrough here was the learning loop. If a picture is showed of X and the output from the machine, so to say the bulb lights up and says it's X, or it doesn't light up and says no, it's 0. If it goes wrong, it was X but it did not light up and it said 0, we actually send an error feedback and we manually adjust the knob. This is what backpropagation does with millions of neurons in today's LLM. So the idea is the same, except for the non-linear activation functions that we have now started to use. This was such a revolutionary idea that patterns could now be, in a way, hard-coded into the system. And this is not an automatic learning happening. It's a human being which is doing this, right? Who is doing this? Slowly, we would want the machine to automatically do it. And those mechanisms were developed. So, from humans doing it to slowly the machine doing it autonomously, this was the revolution. And if the perceptron could do it, maybe we could have tens of thousands of perceptrons working together to decipher complicated targets, which is what a modern LLM is. This is why I am actually taking it up. All the modern LLMs are ultimately a subset of machine learning, right? They are not out of the machine learning subset. Recall the taxonomy. I would love to have your comments on any part of the session today. Keep suggesting things, keep pointing out better ideas, keep recommending books and many other things that you would want to. Go ahead and feel free to do that. So far, so good. So if we go into the full story of Perceptron, which was actually the first time a machine started autonomously adjusting its knob, so to say, to match the given input with its output. So that's a forced explicit mapping happening. So let's see this Hebbian learning based perceptron. And what is Hebbian learning? Neurons that fire together, wire together. Basis that this machine was developed. And the perceptron model is this. These are the inputs. Every input is applied a weight, W1, W2, W3. You sum everything up, pass them through a threshold, and the output is either 0 or 1. But because this activation function ultimately gives you only 0 or 1, it cannot capture the real world truths, which are all non-linear. The real world is very non-linear. You don't have step functions, generally, mostly. So that is why later non-linear activation functions were added, but otherwise the perceptron model remained in theory. I mean, it remains till date. So the perceptron could immediately solve linearly separable problems. And what are linearly separable problems? See, if the data by nature is in two distinct groups like this, the perceptron could draw a clear boundary between them, which in itself is a very big achievement. You're clustering similar data points. But then came a book called Perceptrons by Minsky and Peppert, and it was a mortal shot to the head. It criticized the idea behind perceptrons so deeply that people lost all interest in perceptrons and all investments failed, or rather, dried up, and an AI winter started. So, this single analytical book on perceptron by Minsky and Peppert at that time put paid to the revolution of perceptron. But then later, once deep learning became a possibility and a reality, perceptrons rode back to life all over again. So, this is the learning algorithm that perceptrons use. It is absolutely valid even today. In fact, those who have studied deep learning or today's classification or regression algorithms or how the artificial neural networks are made, even basic ones, would have a smile on the face looking at this algorithm, because this is how even the modern world works, right? So good ideas, they stay on. Good ideas, you can always build on them. Good ideas are always very powerful ideas. This is the story of the perceptron. Enjoy it? You will enjoy with all the other services that we are offering. Make sure you subscribe to a free newsletter, AI for Everyone. It's a wonderful newsletter. Tuesday and Friday, right in your inbox, everything you need to know recently, the developments in AI plus learning. Go ahead and subscribe right now and enjoy the fruits of what our R&D team is doing. Our WhatsApp channel and YouTube channel as well. Thank you so much for your support. So what about the modern LLMs? What neurons do they use? So this is the modern LLM. A hugely complicated endeavor. My job here is not to teach the LLM right now. This is not what today's session is. We'll do it later if you want. This massively complicated structure, actually it's a very simple structure, so to say, an input layer, multiple neurons, an output layer, multiple neurons. Hundreds of layers in between called hidden layers. The only reason they are called hidden is they are between an input and an output layer. Each of them with tens of neurons. Each neuron, the input coming in, gets a weight attached to it and a bias, and everything is added to the next. And every neuron is connected with every other in the next. So this is how they break a problem into the fundamental pixel level and they divide to conquer. This is the magic behind neural network. So that's a separate topic. Our question here is a very limited question. What learning model are they following? Well, very interestingly, they are following the perceptron. Frank Rosenblatt, 1957. So do you see this individual neuron here? This is the anatomy of that neuron. This is exactly what we saw there. Neuron, which is basically nothing but an mathematical construct. There is nothing physical in it. It's just a metaphorical sense we are using the word neuron. And ideally, words like artificial intelligence, machine learning, learning, neurons, these are very misleading words. But since 1950s, these words have been accepted, and that's why the field became so glamorous. Maybe technical words would have been better, because a lot of people actually are confused that LLMs use neurons. They do not. Biological neurons are just too complicated for anyone to work with in the real world individually. So neurons are the basic processing unit. They'll compute the weight, add the bias, apply the activation functions, and once the summed up thing is passed through an activation, you get an output. The reason the neural networks went for non-linear activation functions is real life is non-linear. So how do you capture that reality? You cannot capture it with a step function of Rosenblatt. This may sound slightly technical to you, but you have studied mathematics till standard 10th. You know these things, right? It's not that difficult, truly. Just persist. So let's leave the rest of it and just compare. This was the original perceptron, yes or no? Now you know. This is the perceptron used in 2026. Absolutely. The only thing that has changed, well, you have started using a non-linear activation function. And there can be many, 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 many types of non-linear activation functions. At least 10 are very regularly used. So once again, the job in today's class is not to teach activation functions, but to just tell you that good ideas persist. Amazing, isn't it? $1 trillion industry resting on an innovation by Frank Rosenblatt in 1950s called the Perceptron. It always amazes me thinking about if Frank Rosenblatt could come back and see what his innovation has led to. So now you might question me, from perceptron to the modern LLMs, what has changed? How has that neuron changed? Well, the answer is initially we had a simple binary output. Now we have a complex continuous output. Initially, it was non differentiable, very hard threshold. Now it is differentiable. The tweaking of knobs today can be done via differential calculus chain rule across tens of thousands of neurons. Jeffrey Hinton, 1980s, backprop in practice actually made possible, which led to the deep learning revolution. No backprop, no deep learning, no LLMs, no trillions of dollars, no IPO at 1.5 trillion, no this, no that. Limited learning capability, but now highly trainable. So, modern LLMs are inspired by the perceptron, but functionally they are a very different beast altogether. And massive intelligent systems can be created using that. This is good enough for you to have an appreciation of the continuity of 70 years that we see. And this is how a longer, deeper look at AI and ML should always be effected. Cool. Enjoying the session? Excellent. So, this is where we are. And I wanted to spend a lot of time explaining this fundamental truth of ML. And now we are ready to move one step forward. So, what do we have here? So, in machine learning, every time you have a structured data that you can input the system, you will have the classical machine learning algorithm. 10 or 15 classical algorithms have been working for decades. And irrespective of what happens to the AI industry, the bubble thing and all, the classical ML algorithms will keep rocking. Nothing will go wrong with them. But the moment you move into the territory of perception, language, and generation, then there is no option but to get into deep learning, which is probabilistic and not deterministic. So, in the courses which I run for corporate professionals and the mentoring and the training program that I run, this is the persistent problem, ensuring alignment of AI systems which are fundamentally probabilistic in a corporate environment habituated to having used ERPs which are totally deterministic. That's unfamiliar territory, I understand. Over the next 5 years, we'll learn a lot about it. By 2030, maybe we'll have systems that substantially minimize the probabilistic risks arising from the model. You cannot eliminate it because that's the basic nature of it. So remember this point. This is very important. And let me throw a simple challenge to you. Can you, in the comments thread, quickly explain this point in another way, in a simpler language, and don't use an LLM to do that? To everyone watching this, it's a friendly suggestion from a mentor. The first process of thinking must happen here. Don't jump to an LLM every time. Otherwise, within 2 to 3 years, if you're doing this every time you're faced with a cognitive task, within 2 to 3 years, your ability to think will go down by 90% or more. You'll actually become an intellectual vegetable finished in the knowledge economy. Trust me. And my understanding of the evolving situation of society is maybe in a few years from now, those who are able to think without LLMs might be valued far more by companies and by society itself. So keep that in mind. Keep thinking. That will become one of the Punchlines for the future. Keep thinking. So, which are these algorithms? Here they are. And the comparison with deep learning. So, we have the whole thing ready for you. As I said, there are many algorithms in machine learning. And for all the regular tasks, we always revert back to them. And the moment you have generative and perception tasks, we come back to neural networks. Linear regression. Every time you have to do a price prediction or a forecasting thing because you have trained them with a labeled numerical data. So you have the house or housing price data for the past 30 years for a certain location. You feed all that, you train the model. So any new house data which is fed into it, you know the overall land area, the square footage or the square meterage of that area, how many rooms, other facilities. You can make the initial features 10, 15 feature model, and you put in 30 years of data. And then anyone comes and says, this is the house, so many, the land measures this, ad measures this, and these are the 10 features. You just fill in those. And the price, the potential of the right price basis historical trend will be given by the model in a fraction of a second. So this is classic linear regression. It doesn't need GPUs. It doesn't need artificial neurons. So that is linear regression. Classical ML algorithm, proven, very solid and proven. Logistic regression, spam detection, churn prediction. And again, here you had labeled numerical or categorical data. Very, very actively used. Both of them are currently actively used by corporations. Decision trees, giving approval for loans, basically credit assessment of the applicants, and rule-based decisions. Even today, in many use cases, you have clear-cut rules. If this, then that. If this, then that. If this, then that. If not this, then that. If not this, then that. If not this. You can actually create a machine learning model on the if-then model. Decision trees are a very good solution, but they are prone to overfitting, underfitting and overfitting. Two issues in machine learning. We'll come to that. Random forest. That's the name of an algorithm. Fraud detection and risk scoring. Labeled tabular data. Remember one thing. The type of data mentioned in each of the algorithm boxes is what is needed by that model. If you suddenly switch to unlabeled data, the model will collapse. The model cannot work with unlabeled data during the training phase because that's how it is. The random forest is extremely popular, and on structured data, it does very well. You don't need a deep learning network there at all. Gradient boosting and multiple variants of it. Competitive machine learning, enterprise prediction systems, etc. Labeled tabular. It is industry gold standard for tabular machine learning. Support vector machines, SVM, text classification, small dataset classifications. It can do classification of broad data groups available in a universe. It can do that classification. Slowly declining. K nearest neighbors. This is one of the core idea behind recommendation engines. K nearest neighbors. Numerical feature vectors are used here. Educational and niche practical use, classification or regression. K means clustering. The use case here is customer segmentation or pattern discovery. A company has 10 million customers. What are the segments they fall in based on various definitions you can give? Because once you can see the various segments, a lot of management decisions can be derived. And for that, K means clustering is used. Again, no deep learning required here so far. So do you see that even if deep learning were to collapse, machine learning, a significant part, would survive? That's why in my taxonomy, I had shown many things outside the deep learning thing. Venn diagram. Now, the glamour attached with LLMs and chatbots is so intense that people have kind of ignored these ML things. But then you cannot ignore it's going strong, and All those who learn it, they know how they apply it to companies every single day, tens of thousands of companies. They have evolved, and many of them are now integrated with deep learning. Modern AI is dominated by neural networks, vision, speech, language, generative AI. So either you do large scale label data, but then with the internet, it's not possible to label everything. So it's a self supervised learning. Complex pattern recognition and generation, which the regular machine learning algorithm that we see just cannot do. They are not meant to do that. They cannot break reality into pixels. So if I have the linear regression machine learning model, something that any ML student learns for the first time, the first 2 days, the person will learn linear regression and will feel a sense of joy. Wow, it works. It cannot really break down reality at the pixel level the way a neural network can, because the design is different, right? So, this is a comparative study and a comparative understanding of how classical ML algorithms stand vis a vis the neural networks of today. Understood? Enjoying it? So, there's a lot of wisdom over compiled over so many years. I'm trying to put everything in as easy a way as possible for you. Many teachers have actually reached out to me and they said that we are very happy to see these and we would like to use these in our classes from time to time. Go ahead, be my guest, enjoy. If these are free resources available here on YouTube, go ahead and tell me where I can improve, and maybe I'll bring those sessions, improved versions as well. So, how does ML go from data to models and outputs? Once again, fundamental question. So far, so good. There are ML algorithms and there are perceptrons and there are neurons and blah, 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 blah. But ultimately, what happens to the data once it is fed into an ML algorithm? What happens inside? And the hyperspace thing we had initially touched upon? Absolutely, we are coming to that. Once again, remember, human brain is not designed to see and experience anything beyond 3 dimensions. So I truly believe that it's not possible for anyone to experience 4 dimensional reality. If you have, you should really tell us in the comments. It would be worth learning from you. Right, boss. Let's move on to how does ML grow from data to models and outputs. This is how. You can feed structured tables. Machine learning loves it because the job becomes easy, right? Everything is neatly relationally created. You can input unstructured text. You can input images. You can input audio waveforms. You can input continuous sensor streams, temperature, pressure, vibration, stock prices, maybe. You're getting the feel. Just focus on the leftmost side of it. Structured tables, unstructured text, images, audio waveforms, sensor streams. And here are the ML systems. So now we have chosen whatever media we wanted to. And remember, in normal ML algorithms, you only feed data in one mode. With modern LLMs, a real holy grail is multimodality. The LLMs can ingest data in multiple modes at the same time, which actually is quite an achievement. And then to make sense of it, and then to give an output which is relevant to it. So the ML system starts processing here. The first thing to do is feature extraction. In feature extraction, the key features as the ML algorithm designer or the user wanted, they will be put in a vector space. So if you give an unstructured text, it will do word embeddings. So this is a whole topic in itself. I'm not getting into the technicals of word embeddings. Just understand it in a simple way. An LLM takes in all the internet worth of text, millions upon millions of words. What it does inside in its own space, let's call it mind. It has no mind, but let's call it that. In the LLM's mind, similar words are clustered, grouped, kept together. So, woman, queen, ruler, lady, female, these words will be together. Man, king, ruler, autocrat, male would be closer. Of course, assuming the data set is unbiased. Similar meanings, the semantically similar words, would end up getting clustered closely so that the final probabilistic output number goes up. This is made possible via systems that do word embeddings. A reason our LLMs today are so powerful is they are very good at word embeddings. In a hyperspace where millions of entities exist clustered logically together. So, that in a layman's language is word embedding. Got it? If you feed in images, then the system has to take out the edges, textures, maps, CNN layer, convolutional neural network layers. If you give audio waveforms, spectrograms, and others, if you give sensor streams, time series features, and then it goes inside the feature space where pattern discovery has to happen. Because the goal of doing all this, the reason for doing all this, the objective for doing all this is to discover the patterns. And then it goes in the feature space. Similar things get clustered closely and patterns are found. Image feature hierarchies or fraud detection patterns or customer clusters. Everything in this high dimensional space starts operating. Is that clear? Any questions? So the feature space actually can be a very, very high dimension space, a very, very high dimension space, which is also called the hyperspace or the feature space. Then the pattern discovery happens here. Fraud rules, customer segmentation, image recognition layer, decision boundary separating two classes, and finally deployment for the real world happens. So some of this might have sounded a bit abstract. When you actually start making an ML model with some of the free tools available on the net, you will see in practice how it happens. We'll do that in some of the later sessions as well. These are overall masterclass sessions to orient you toward the theoretical and actual practical foundations of what is going on. So be patient with me. These things take time. Did you see the video I made on World Labs? Spatial Intelligence World Labs by Faifai. There's a beautiful video I made in the AI Affairs playlist. The next leap of LLMs could be global world models, which has been a consistent criticism of LLM. So I just thought I'll make you aware of it. That could become a big thing in the future. And so this is machine learning, feature extraction, feature space, and the trained model. It would be trained millions of times over the data to extract all the patterns properly and adjust all the parameters to have learned those patterns well, so that when a new pattern comes in, it can fit it properly without underfitting, overfitting. If you know nothing about AI, my course AI like IM10 is exactly for you. Absolute ground zero, AI like IM10. If you want to get a good understanding of generative AI and you know nothing about it structurally, the course Gen AI like IM10 is for you. If you're a corporate executive who wants to intensely and quickly learn AI from a strategic perspective, AI Force Multiplier is for you. And if you're a CXO needing long-term hand-holding, check out CXO AI Mentoring. So what are the four basic paradigms or models in machine learning? It all comes from data, right? We have seen that. Supervised learning, labeled data. Unsupervised learning, unlabeled data. Semi-supervised, a small part is labeled, but largely 80-90% is unlabeled data. And self-supervised, data is its own label. Large LLMs reading the internet today would actually be using self-supervised learning. And then you can have reinforcement learning mapped on top of all this. So the four basic paradigms in ML are these. Actually, LM also fits learning machines, machine learning and learning machines. Amazing. So what happens in supervised learning? Now, even if you are a beginner, questions on ML will definitely come from such basic concepts. So I have tried to keep it at the bare minimum because this is an AI startup for you, right? As far as the learning experience is concerned. Supervised learning has labeled data. For example, you have thousands upon thousands of pictures of cats in different positions, different types of cats, and similarly for dogs. I don't know, every time they talk about dog, they always get Golden Shepherd. I don't know why. Is it a Golden Shepherd or a Labrador or a German Retriever or so golden retrievers are such beautiful creatures and they all look the same. It's a conspiracy. They resemble each other. Probably they have figured out how to fool human beings. Anyway, so model learns from explicit examples with known answers. So you already have labeled pictures, thousands and thousands of them. You cannot train them with just 10 or 100. Machines don't get trained that way. And the goal is the next time I give you an image, tell me whether it's a cat or a dog or both are there or it's a giraffe or a donkey. So accordingly, you'll have to feed in that many data sets or pieces of data depending on how much you want it to be good at in terms of recognizing. Input data plus labels, model training, prediction. So you can do it for image classification, even for email spam filtering. Supervised learning works just fine. Then you have unsupervised learning, that is unlabeled data. So whenever data cannot be labeled either because it's too painstakingly tedious or costly to label the data set, or it's just not possible to do it, then you have no solution but to take recourse to unsupervised learning algorithms. The model itself will find patterns without labels. So this is one meta level, one level up. Our goal is to discover inherent groupings, k-means, PCA scatter plot. Don't go too deep into this. Just understand that, okay, this is how it works. And it'll end up structuring very clearly and showing you these are the customer segments actually buying your product. So then you can change your marketing strategy, your budgets accordingly. Anything that you see here was because there was some real world business need or scientific need or some political need somewhere to have a system which could analyze data. All of ML is nothing but data analysis and trying to find meaning from vast troves of data. Semi-supervised. What to do if you have a very large data set, but only a small part of that can be labeled, and the most and largely 80-90% remains unlabeled. That is SSL. Got it? So you do that and you do the model training and improve predictions pop up. Web content classification, speech recognition with very limited transcribed data. And neural networks have been wonderfully proficient at doing it. This is why after 2017, 2018, the world took to LLMs in such a big way. So that was semi-supervised because half of it, or rather 10 or 15% was labeled. This is also an SSL, but this S is self-supervised learning. The data becomes its own label. The model ends up generating labels from the data structure. So if a model can do that, it is actually creating very rich representations because there is no hand-holding happening here. So that is self-supervised learning. Input data, a mask is applied, and the model discovers that fill in the blank here should have been cat. Language modeling, BART, image in painting. So these are slightly complicated terms. Forget that. Just remember that there's a thing called self supervised learning where the model will generate its own labels. And then reinforcement learning can be applied to all of them. So these are the machine learning paradigms. If you decide to make a career in machine learning, these are the things you'll be learning for a few months, making models, applying them to data, learning from the data, and so on and so forth. So, which are the top 6 machine learning algorithms? If somebody were to ask me, because this again, as we said, for machine learning, we need to know some of the basics at least. These are the top 6 machine learning algorithms. We saw them earlier also, right? But now we are focusing purely on these and not doing any comparison with a neural network, etc. That is not our goal right now. We are just focusing on these machine learning 6 top algorithms. Linear regression always will remain number one. This is a predictive task. It plots a regression line and tries to see where the next point would fall on that line. Credit scoring, predicting house prices, etc. Decision tree, we have already seen, can be used for both classification as well as regression. Identifying disease risk, medical diagnosis. And once that diagnosis is done, in America, what they are doing is, if you are doing a population level diagnosis using machine learning system, then you potentially call up the people where you see a huge risk of particularly catching a certain disease 3 or 4 years down the line basis historical data fed into the machine learning model. So very funny and tragic situation arises when people are called and informed that based on the machine learning model we have, our analysis and all, we think you might be prone to this particular disease. All his happiness is lost. The glorious uncertainty of life is lost. But then if the person can do some maintenance, the person can take some preemptive action, well, then it's worth it, isn't it? So those are very sensitive areas where a lot of human sophistication is needed in communicating to those people. Random forest or ensembles. By majority vote, you could take an average from the individual random forest and then do the market segmentation. One use case. Support vector machines to divide to clearly create a boundaries. So abnormal behavior can be identified. Neural networks, deep learning, you already know. Hundreds of applications now. Every conceivable application is there. And clustering, K-means. So this can help you actually identify clusters so that you know what are the behavioral groups within your customer segments so that your marketing, A/B testing, etc. can happen accordingly. So now you see why non-technical people also need to learn some of these things, because your marketing department will ultimately come for the budget, and once you grant the budget, they will say this is how we are going to plan the next year of activity. If you can empower with these yourself and the teams with this, maybe the returns would be significantly higher. That's all. Instead of carpet bombing, maybe you could do very specific targeted marketing. And all this is now industry standard. There is nothing new I'm telling here. These are all industry standard practices. A beautiful graphic that explained the whole story, isn't it? And you can try to dive deep into it to find more, to learn more. I leave that to you. I recall the scikit algorithm cheat sheet once again. If you have less than 50 samples, God bless you. Go back, get more data. Machine learning is not meant for less than 50 samples. The output will always be disastrously wrong. If you have more than 50, then either you are predicting a category or you are not. If you are predicting a category, either you have labeled data or not. If you have labeled data, either it is more than 100,000 or not, and so on and so forth. This is a wonderfully scientific basis of understanding in your head, okay, this is how I decide as a manager which model to apply to my data. Every company will have a different scale and intensity of data. You can directly use this cheat sheet and decide which 2 or 3 algorithms are actually relevant for you. That's the power of such a cheat sheet. Actually, what happens in the real world is that managers build their own cheat sheets over time, because having done things, they know it works, it doesn't. So they have their mental models or even paper-based cheat sheets like this, and they can almost instantly, experienced managers can say, "Okay, for this situation, this data, this condition, this circumstance, this will work the best." Scikit people have only tried to theorize it properly in one sheet. So I recommend that you take a note of this and learn from it. It helps. I'm going a bit slow because I want all of you to digest these things at a very basic level. Okay. So, what are the four things you saw here? Classification, regression, clustering, dimensionality, reduction. In classification, you classify it as either a cat or a dog. In regression, you end up predicting the price for that house. So, it will be a continuous number line. In clustering, you create groups. And in dimensionality reduction, a given complicated set of data can actually be normalized, standardized, and dimensionality reduced for making better predictions possible. I believe this should be enough for this particular angle. Now we come to hyperspace. Yes, interstellar movie, wormhole, hyperspace, traveling across galaxies. Amazing. Traveling from one star to the other in a few moments. In the real world, we still haven't come across any wormhole that could take you through cyberspace, hyperspace. But in LLMs and in machine learning, you have hyperspace of hundreds of dimensions, whereas we humans can only see three. But these machines end up working with hundreds. Why? Because it is mathematical. There is no physical hyperspace here. This is a purely mathematical hyperspace. So let's see what this is. Recall our discussion of how we make ML work. You recall that? Data is collected, converted into features, the model is asked to make predictions, errors are measured, and the model updates itself. A very simple process repeated millions of times, again and again and again and again and again and again and again, till the patterns are properly deciphered and the model is so called trained. Got it? This is how it happens. Now we come to the hyperspace patterns. This is your raw data: text, images, numbers, signals. You do all the processing. You see, data has to be cleaned, deduplicated. There's a whole curation process. That's why you have dedicated data engineers, data scientists, data analysts, all doing a different thing on a given set of data. Raw data can never be fed. When we say raw data, we actually mean raw data taken and then taken through a process of taken through a whole step of processing and then fed into the ML system. Otherwise, the ML system will go mad. In data preparation stages, you attach the features and labels to it, measurable attributes. The features are all measurable attributes that you are interested in. The pixel colors, red, blue, green. So you might want to see it in three. Word count, temperature, all of them can be features. Because the model only understands numbers, right? And labels are the outcomes. Cat, yes or no. Spam, yes or no. Healthy human, yes or no. The answers for the model during the training, those are labels. So features are the attributes of the data that you are interested in, and labels are the final correct answers that you would expect. So you take raw data, process and transform it, and you create the space. This is the feature space. If there are more than three features, 4, 5, 40, 50, 400, 500. So if you have 29 features in your data, then this hyperspace will be a 29 dimension hyperspace because each feature is one dimension. Is that clear? And because we can neither draw nor envision anything beyond X, Y, Z, three dimensions, so our problem is Even for an n dimension hyperspace, we have to ultimately show it in just 3 dimensions. What to do? Because it's not physically possible for us, but it exists, right? In mathematical space, it exists. And in this n dimension hyperspace, our machine learning algorithm has to find the boundaries and the clusters and so on and so forth. So there could be 55 clusters of customers in your overall customer ecosystem. And for each, there is a feature. So it's a 55 dimension hyperspace. You can't see it, but the model will very clearly separate them in the 55 dimension hyperspace and give you the output for it. That is why machine learning in AI has become so important. And with multimodal systems or multimodal systems, their importance is only getting more and more embedded into our day-to-day lives. Is this clear? So that is machine learning. I'm not actually building a small ML model here because that's not the goal of this lecture. Maybe I'll do it in some other playlist. Here I'm trying to explain and give you a very solid theoretical foundation to the whole game here. Got it? And once the model has created these boundaries and all, any new data point that you feed into the model will get fixed somewhere. And so the prediction will be, it will be this kind of a customer. So you can mark it accordingly. That's the idea. Got it, ladies and gentlemen, boys and girls, learners, students, CXOs, professionals, managers, everyone, welcome. Feature space is a 2D example here, which is absolutely correct. And feature 1 was height, feature 2 was weight. So somebody gave me 8 data points, okay? Cat 1, 2, 3, 4, dog 1, 2, 3, 4. For each cat and each dog, I was given the weight and I was given the height. So what was of interest to me? One feature, weight of the animal, cat or dog or donkey or giraffe. And 2 was the height. And now I start plotting because I only have 2 features. So my hyperspace is of what dimension? 2. And if my hyperspace is of 2 dimension, this is the regular XY graph we have. First feature was height, second feature was weight. Remember, features are measurable attributes of interest to us against which a new data point is going to be evaluated. Is that clear? So now data points were plotted and the number of dimensions is equal to number of features. So you're wondering, how does this work? Suppose I give you a new data point. This is the weight, this is the height. What is it, cat or dog? Wherever it falls. So if the point falls somewhere here, then the machine learning model will say, I am 97% confident it's a cat. If the point will fall somewhere here, it's a dog. And if the point falls completely off the chart, the machine learning model will go astray and make any nonsensical prediction because it was not trained for it. This is why you need tens of thousands of examples. This is why neural networks are so hard to build. Are all the dots connecting? Literally, we are connecting the dots here. This is a very nice example actually for students to learn. So this is the feature space of 2D. Now this is the feature space of 3D or a hyperspace where n is equal to what? 3. Now suppose for the cat and the dog and the animal, the first feature was height, second feature was weight, and the third feature was age in years. Now, you do not have a single linear separation, a line which could separate them. For example, here, you could have a separator line here. In a 3D space, you have a plane, a flat surface, a plane, which becomes the separation boundary. Boundaries are absolutely critical in machine learning. In fact, that is the name of the game. So we have very intelligently, very softly introduced the concept of boundaries also. Enjoying the session? Be with me till the end. Make sure you subscribe to the newsletter. It's free Tuesday and Fridays. Beautiful AI articles in your mailbox. Make sure you join our WhatsApp channel. Make sure you subscribe to the YouTube. Accept my thanks. Thank you so much. So this is the plane because we have three parameters now, actually features, and the plane can then be used to do whatever analysis we want. Now the problem is the moment two more features come in, the color of the animal. So you had height, you had weight, you had age in years, and now you have color. So you have four dimensions. My mind can't think of four dimensions. Impossible. No one can. No human being can. If some animal can, I don't know, because there is no way of me experiencing an animal brain. No way any organism can experience any other organism's brain. So this is the first feature, second feature, third feature, fourth, fifth, sixth, seventh, eighth, ninth. You can have 100 features. So there is the decision hyperplane, n dimension separation. You cannot see it, but mathematically it exists. What is the proof it exists? You give a new data point. Now you know what kind of an animal it is and the 10 features of that. You just feed it into it. If the output of the LLM is perfect, it is working. If it is perfect the second time, it is surely working. If it is perfect the 2000th time, it is definitely correct, provided it was trained using millions of examples. Have you now understood hyperspace? So I'll explain it in a very simple language now. Hyperspace, that very funky concept. When you train a machine learning model, you feed data into it. The data pertains to real world. Whatever objects you are feeding the data of into the model will have features, one feature or two features or three features or 3000 features. The number of features is equal to the number of dimensions in the hyperspace or the feature space. 2 and 3 is fine. We can see, we can draw. 4 and onwards, we can only mathematically work at it. And it could be in thousands. The feature space can run in thousands, depending on how complex, how rich, how deep you want your model to be, and how much money you have to spend on training. These are not easy things. So you can actually rent cloud space right now and start training a model. And in a few $100, you can actually train some complicated machine learning models also. It's not impossible. People are doing it and doing it quite successfully. Someday we can give a live demo of that as well. So far, so good. Hyperspace absolutely clear. So this is the real game. 10, 20, 30 dimension hyperspace where very rich analysis mathematically happens. As I'm fond of saying, anytime somebody says AI is magic, always correct them. So it's mathematics, not magic. It feels magical because anthropocentrism, right? But it is actually mathematics. So what did I just say? Can you explain in the comments thread? That would be lovely. So can we see a full ML training cycle in its entirety from start to finish? Absolutely, you can. Here it is. Oh, wrong request. We were better off without seeing this. Okay. So if you are actually launching a complete ML project in your enterprise, then if you're talking end to end, this is how the whole thing is going to work. As you can see clearly, this is where the story always starts: raw data. Data cleaning and pre-processing, data split, because you need to split it in training, validation, and testing data. So let me explain that. If you have 10,000 pieces of 10,000 input data pieces, elements, points, data points, and you feed all the 10,000 to your machine learning model during training, there's a huge problem. It will memorize everything. So the moment you give the 10,001th data point later for testing whether it has learned, it will not be able to do much because it has now overfit itself to that data. We don't want overfitting. We don't want underfitting. We want a general fitting. So overfitting happens if the entire data set is fed. So that is why you break it into three. What are the three? Training set, validation set, and later testing set when you don't do back propagation. And then the remaining things happen. There's a lot of many steps involved. Hundreds of people are involved in this entire process. And now, over the past 10 to 15 years, the processes have become very standardized. A lot of that has gotten automated also because of agentic AI and other things. But still, once a base model is created, to actually fine tune it and for commercial deployment to further fine tune it, hundreds of human beings, human contractors are needed to actually work their magic on it. The only magic in LLM is what the humans do to it. Otherwise, it's pure mathematics, as I always say. So the rest of it is for your enjoyment. Look at it, feel enjoy. And if you are not able to sleep properly in time, you could come back to this, listen to this for 5 minutes, and you'll have a wonderful sleep. Of course, some nightmares will keep arriving. So sorry for that in advance. What are the downsides of ML? Show us the risks now. You have been talking so highly of ML, but are you absolutely certain that ML has everything positive and nothing negative, and I can bluntly go ahead building my own ML model and things? Well, no, not at all. There are many downsides. These are absolutely proven downsides. I'll explain all of them, and then we'll do a revision of the whole session. The first major downside is bias. Group A and Group B. Just look at how poorly represented Group B is. So the model will think, quote unquote, think during recruitment that Group B should always be only 10% of the overall recruitment universe. So even talented people from Group B may get a negative rating because the model has been fed data which is hugely skewed. Yes, I know what you're thinking now. What if this is the reality of the 3D world? What if this is how the world is? Absolutely. I have no problems with that. This may be the real world. But when you feed this data into the ML model to judge a potential HR interviewee's capabilities, don't blame the model then for giving you completely biased inputs. So then how to tackle this? Well, remove bias. At least feed in data which is somewhat similar, not this skewed. Otherwise, it's all a disaster. So this is a biased data set, Group A, Group B, a biased data set. And this is a problem that most companies over the past 3 to 4 years have now reported. And so what do companies then do? They undertake a massive revision of the databases. And the companies are not at fault. The real world was simply reflected in the data sets, which they innocently fed into the machine learning model. But while a human HR manager, as per the new DEI policies, diversity, equity, inclusivity, etc., could apply her discretion and avoid bias, the machine cannot because it was trained with the bias data. So remember, bias is the first sin. Ab initio, it destroys the ML model. So please work on data in the sense of removing bias. And then there are very structured methods to remove bias. Yes, that in itself is a field. Bias removal. Explainability challenges. I have already discussed that with you earlier. You recall the black box model? LLMs suffer from an explainability challenge because you do not know what cluster of neurons of the total set fired to reject the loan application of Mr. X. And if Mr. X questions, all you will have to say is, well, this model said no. But you cannot go in and find out. So explainable AI is a field of research. A lot of work is happening. Over the next few years, maybe they'll be able to find answers to this problem because the box is actually black. You cannot dive in. It's amazing how humanity actually surrenders to technology in a way, even technology which we don't understand, simply because in the testing scenario, we found that the outputs were largely acceptable. So we are assuming that forever the outputs would be largely visible and a commercial model business has been built around it. What if it won't? Well, then some human being somewhere will pay the price and then the system will be improved. That's it. There is no other angle to it. Privacy concerns. Data leakage is a very real risk. This is why I always advise people never ever write anything on an LLM platform which you will regret being public tomorrow. That's it. Anything you write, any data you share, any number you share, any confidential password that you share, if you are okay with that thing becoming public tomorrow on the internet, go ahead and share, no problem. But if you are uncomfortable with it, the answer is simple: do not share. Adversarial risk. So, what exactly is the adversarial risk in machine learning systems? Very simple. A model has been trained to identify pandas, beautiful creatures. A miracle of nature. They actually shouldn't exist, but they do. Such lazy bums. So, a model has been trained to identify pandas. I am a bad faith actor, a malicious actor, and I add noise to that model, some strategic noise in my input. The model may start misclassifying pandas as hippopotamuses or black bear or sloth bears. By the way, sloth bears are very dangerous creatures. They can even kill a tiger. I saw this stunning video on YouTube where a tiger, a full grown male adult tiger, attacked the sloth bear, long black hair, thinking that some struggle and the sloth bear would be dinner. The sloth bear fought back. And suddenly, out of the blue, a second sloth bear came running, and both of them butchered the tiger. It died. So, sloth bears are dangerous. Anyway, so in adversarial risk, what happens actually is there is a danger that a model can be fooled by a bad faith actor. It can be attacked by manipulating the input data. If the data is normal, perfectly fine, but a bad faith actor can add strategic noise to that data and the model is fooled and all its explanations and predictions go haywire. So here the panda starts saying it's a given. This is a harmless case, so there is no problem. What if this was a policing ML and people would be incarcerated because of this? That would be a disaster, right? It's actually happening across the world. There is a real risk. So, adversarial risk happens when you intentionally attack a model and it loses its normal behavior because small intentional changes, which may not even be visible to the human eye, can make the machine learning model go bonkers. So, cats will become dogs and pandas will become gibbons. So, now you might question me, where does this risk exist of models getting fooled? Well, across the ML universe. So the good ML designers know this and they try to preemptively minimize the risk. You cannot eliminate it, but you can minimize. For example, in image recognition, you just alter the pixels slightly and the models can be fooled into identifying pandas as gibbons or cats as dogs or monkeys as donkeys. In spam detection, slightly you can tweak the words and you can bypass the filters because they were very rigidly trained. They were not flexible enough to see the generality of spam. So a smart operator can tweak the words a bit and escape the spam filter. In face recognition, you could slightly trick using some pixel or some other object the face recognition system. In self driving cars, if a sudden new road sign comes up, the system of that self driven car can be fooled completely and an accident can happen, or the car may screech to a halt suddenly if that's how the system prompt says. In medical machine learning, it can actually be devastating. If some wrong inputs are given along with a proper CT scan, some malicious pixels are also embedded. All the wrong medicines will be recommended to patients. So, yes, the risks are immense. There is absolutely no doubt about it. Is that clear? So, there are various types of adversarial risks actually. So, what are the various types? It will help us if we can spend a minute on this because this is a very crucial insight. Adversarial risks in machine learning, where you end up labeling pandas as gibbons, which is a harmless case, but then there can be very deadly cases, as I explained. It can happen in image recognition, spam detection, face recognition, self driven cars, financial and medical machine learning, right? As we saw. Why is it risky? Because the model actually trusts patterns, not intent. There is no system in the world where a model can be told that such a human being has a bad intent. The model cannot see you. The model doesn't know that you have come with bad intent, or the extra pixels you suspiciously supplied with an image are bad intent pixels. The model has no way of knowing it. At least till date, it doesn't. Attacks can be cheap and automated because now people are actually using LLMs. Errors can go unnoticed for a long time in very large systems, and there can be security, safety, or financial damage because of this. Common types, adversarial, I have already shown. Data poisoning. Now, training data itself can be manipulated by some disgruntled employee or staff member. So the whole model ends up getting trained on faulty data. How will it ever perform in the real world? Model stealing. If attackers know how your model actually works, they can find vulnerabilities and exploit. Evasion attacks. And of course, you must have heard about prompt injections also. The prompts can actually carry extremely malicious lines of code which do jailbreaking in the pattern or in the model. And how do you reduce? You actually do a lot of adversarial training and tweak the model to identify and accordingly reject adversarial attacks. Input validation, sanitization, model robustness testing, ensemble models, monitoring suspicious inputs. It's an evolutionary rat race. The attackers will come with new ideas and the defenders have to accordingly up their game. This is how Mother Nature has operated for millions of years. This is how it will be for millions of years, assuming humanity survives. Got it? Then model drift. A model's performance can simply drift over time because of the necessary timely corrections not being made by the corporate bosses. A lot of corporates think that AI investments are a one time investment. You do it and you sit back, relax, and enjoy the profits multiply. Unfortunately, AI systems require continuous tweaking, monitoring, upgrading, model drift rectifications, and a team dedicated has to keep looking at it. Otherwise, the performance drops drastically because the accuracy goes down in time. And finally, fairness and regulation. The model may simply fall foul of regulatory agencies. See, there are multiple AI frameworks in the world. They are called AI frameworks. There are whole courses available on AI frameworks. So, what are AI frameworks? At the top level, you can have an ML ops framework, you can have a governance framework, you can have a risk framework, blah, blah, blah. And basically, there are 8 top frameworks in the world. You have NIST framework from America, you have European Union AI Act, you have OECD framework, you have Google framework, you have Microsoft framework. So there are 8 top frameworks that any corporate person should know because any AI project has to fit into those frameworks depending on which country you are in and so on. India in recent times has issued new guidelines, BIS standards for AI. More on that later in a separate playlist. So are the risks now clear? I hope you enjoyed learning this. So this is the downside. And unless and until ML model makers learn the downside, they cannot truly make models which are robust, capable of tackling problems, and capable of offering the right kind of output. Is that clear? Any doubts? So, what does the future look like? Well, these are truly big ideas about the future. I run a special playlist, AI and the Future of Humanity. Check the videos in that playlist. There I delve deep into these big issues. So you'll find a lot of good material and we'll keep on populating these free resources on the YouTube very regularly. and also link it with the Insights website where you have hundreds of articles to read. So it's a good resource for you, anyone who wants to learn right now. What will be the future of humanity with AI and ML? Well, we don't know because for the first time we have actually created something like intelligence. If you saw lecture 2 in the playlist, I had given a whole list of books which have speculated on this. Remember Life 3.0? Remember Super Intelligence? And many, many more such books. I showed it, physical copies from my library. Reading books remains the best way to actually understand things. Unfortunately, many people just read the cover and move on. And then they talk about the book as if they have read it. I admire that confidence completely, totally. Now, so that's the machine learning model without data. Actually, rich in confidence. For the first time, we have actually invented intelligence. And the downside is that the intelligence turns out to be malicious. The upside is that the intelligence remains completely subdued, slavish to us, and subservient, which is good for us. And it doesn't ever develop a consciousness of its own. We don't know what point of time it would be in the future where an invention of man which actually become conscious. So far, nothing, zero, zilch, nada, nothing. If ever sparks of consciousness are seen in AI systems, then we'll start talking about maybe general intelligence AGI, and then maybe AGI becoming very smart and turning into ASI, which is a self recursively improving intelligence. That world would be different because then that would be mankind's last invention. The ASI will do everything for us. Will a few human beings control it, few governments, or will it be open to the entire humanity? These are all open questions. And humans are unpredictable creatures. Entire societies can rise in revolt against AI. One doesn't know. The future holds the answers. At the most, what we can do for now, make the most of the AI revolution which is upon us. Try not becoming irrelevant in this. Keep learning, and keep doing the best we can to make others also learn and not become irrelevant. So, as an individual, this is the best you can do. This is the best you should do. So, the future of machine learning, multimodal AI, neurosymbolic hybrid models, because symbolic as well as neural both have their severe limitations. Autonomous robots and collaborative systems, personalized AI assistants, scientific discovery. Actually, you will be very happily pleased, surprised in fact, to know that after a long drought, a new antibiotic molecule was discovered using ML and AI systems. You know very well that humanity's arsenal of antibiotics is running out. We now have AMR and we have pathogen resistance and all. And finding new antibiotics is a very time consuming, costly, and a very risky. So now AI and ML is being used to actually identify potential antibiotic molecules, and one such has already been successfully identified. This validates the notion of the optimist that AI and LM may save humanity. I don't know whether save humanity, but green AI, edge intelligence devices, on device AI that all of us now actually have at a rudimentary level, all this will grow. Some people also talk fancifully about creating a civilization on Mars. Not happening, boss. Digitally downloading your brains. Not happening, boss. It has to be embodied. Otherwise, there is practically the brain will go mad the moment it realizes it doesn't have a body. What will it do for the rest of eternity? Isaac Asimov's last question and last answer actually address these issues. So the future is full of promise. The future is full of pitfalls. If techno capitalism is the only moral guiding light of AI innovation, we may be headed for a disaster. Techno capitalism and techno oligarchies alone cannot be allowed by societies and governments to take charge of machine learning, AI, intelligence creating devices, AGI, ASI, because their only incentive will be to maximize personal profit at any and every cost. We can see that in the way data centers are being put up across the world. Many of the top companies want to do that with India because they know they can easily get away with anything while putting up the data centers. That would be disastrous for the environment unless regulated very hard. So these are big questions, and data centers are the backbone of everything. We don't see them, but they are the ones running the whole show, actually. Yes or no? So, my dear friends, this is a historical summary of everything we studied today. I will quickly take a revision of the whole session now. But this is the evolution of machine learning from the initial rules based systems to generative AI of today. This was symbolic AI. Then came the massive breakthrough in perceptron of Rosenblatt. Then came its end also 10 years later, but then again after 80s. Nearest neighbor algorithms, decision trees, support vector machines, LXNet, which actually aced the ImageNet annual challenge by Fei Li, transformers, large language models. This was the evolution of algorithms phase. This was when GPUs actually slowly came into being and more compute became available. This is when big data arrived. And this, of course, is the coming together of everything: big data, big compute, latest algorithms, and a massively cheap and super fast internet, and a mobile handset in every hand. All this made generative AI possible. So now it is in a self improving loop. Continuously, recursively, it is adding to its strength. This is what happens with systems when they go in this loop now. What a beautiful timeline this was. I hope it helped you. Within machine learning, these are the key terminologies that you should be knowing, learning, using. Yes or no? So it's time for us to very quickly take a look right from the beginning what all we studied today. Ready? Ready for a quick 5-minute revision? Make sure you have subscribed, make sure you have liked, shared, and also made a beautiful comment. Okay, dear learners, here goes. So, this is where we started. This was our third session in the playlist. Total, there will be 7 beautiful sessions. Anyone who actually undergoes this training at a basic level, you will know so much. At least you will be thoroughly clear whether you want to pursue AI anymore or tata, goodbye, no more. That clarity will arrive. That's my promise. And I am certain many of you would want to continue for the basic reason that, well, there's no escaping it now. We saw broadly what could be a learning chart for any ML enthusiast. We went back to our beautiful billion buddies chart of AI taxonomy, and I tried to place in context whatever we were trying to learn today in terms of the machine learning being a part of AI. And you can see how huge the entire artificial science is, artificial intelligence science. Where do we really use ML? We explored this question most honestly. We tried to find whether ML is actually used. And I said, yes, bro, ML is there everywhere. And these were the examples we saw. As I said, just the tip of the iceberg. Practically any large system you will see in the world today, it is ML. You may call it AI, but then most of AI is actually ML in terms of practical applications. In fact, most of DL also in the backend is ML with a neural net in the front end. Is that clear? Exciting, right? Then we became our 10-year-old selves and we asked ourselves, how can computers learn like a 10-year-old? And all that we learned was very simple. Show more and more examples and tell them what it is, tell computers what it is, and then ask a question. And if it goes wrong, correct it and do it again and again and again and again and again, more and more and more examples, till the computer ends up giving the right answer. But with human beings, it's very different. There are innate priors. So now let me spend a couple of minutes explaining a fundamental kernel of truth about human learning. This is very, very interesting. Pay attention. Inductive reasoning versus deductive reasoning. The moment we are born, our brains have to start reasoning around the world it finds itself embedded in. It is initially very confused, it starts crying, and then it gathers itself and slowly begins understanding. Humans do a lot of inductive reasoning because there is no possibility of doing deductive reasoning. What did I just say? Inductive reasoning. X died. X was a human who died. Y was a human who died. Z was a human who died. All humans die. This is how humans learn. We see specific instances of a phenomena happening. He died, she died, he died, they died, everyone dies. From specifics, we come to generalizations. It's a huge strength of humanity. This is how we evolved over millions of years. Because if we go by the deductive reasoning route, we will perish as a species. All humans die. I'm now doing deductive reasoning. All humans die. X is a human, so X will die. But the problem is, 2 million years ago, how would my ancestor, primordial ancestor 2 million years ago, know that all humans die? For that, he would have to keep looking all around till he's the last guy left and everybody dies. Then he'll say, okay, I will also die. Our species would perish. So, deductive reasoning is not how humans work. Actual real world growth in evolution. We use inductive reasoning. He died, she died, they died, oh, everyone died. And so early humans would have gotten an incentive to keep running from predators. Lions kill, hyenas kill, wild dogs kill. These carnivores all kill. Run! Let me wait and watch whether that pack of wild dogs kills me or not. Because lions kill, tigers kill, but how do we know wild dogs kill? The sensible guys ran for their life because they had done inductive reasoning. If you fall into the trap of deductive reasoning, the species would perish. This is a very simple way of looking at how reasoning works, because reasoning in LLMs is a very key issue. So remember, universal and general truths are impossible for a human being to establish ever, in general. And at a species level, evolutionary level, where you are in a predator-prey relationship, deductive reasoning will never work. It is inductive reasoning, get up and run. That's the idea. So I just thought I'll explain this concept and you can then do your own research. It's a beautiful field of research. Then you talked about what is the most basic process in machine learning. This is what we saw. After the data has been fed and all, make a guess, check the answer. If it is wrong, learn from mistake, adjust the knobs and parameters, try again. Millions and millions of times. This is why there is no magic at all. There is so much of grunt work happening. Where is the magic? Where is even the idea of a magic? Got it? Then we beautifully saw the concept of data defined by features, 2 or 3 features our mind can see, draw either 2D plane or 3D structure and a plane inside, making the boundary line, and any new data point coming and getting classified. And beyond 3, you have a hyperspace. Mathematics can handle it. So you can have a data with 15 features on data points. You can't draw it on a piece of paper. You can't have 15 axes, right? But the hyperspace can, and it can draw the boundaries, and you can immediately say that customer will fall there, and immediately the model will say. Otherwise, it would be very difficult for you and very manually time consuming. That's the beauty of ML. Understood hyperspace? We also saw the whole range of ML algorithms, scikit-learn cheat sheet. We saw the 10 big innovations. Each of them is worth a 1 hour lecture, but my focus here was on perceptrons. And this, initially, the McCulloch-Pitts neuron, Hebbian learning, neurons that fire together, wire together, and early control systems. And then I made an appeal to you to subscribe to the channel, like and share the videos, make a comment to help the channel grow. And then came the daddy, Perceptron, which is still in use today with many modifications. Frank Rosenblatt, long live. Modern LLMs, every neuron is just a futuristic adaptation of the humble Perceptron. I gave a very clear difference between the two in terms of activation function instead of just a 0 or 1 step function. You can use that even today if your data is basically linear. But if it is non-linear, there is no hope if you don't use the more modern activation functions. So classical ML coexists with deep learning today. Then we saw the comparison, we saw the feature space, hyperspace, we saw the academy courses, and you have decided to enroll in at least one of them. Thank you so much. What are the four basic paradigms? Which are the top six machine learning algorithms? The beautiful concept of hyperspace. This was a very, very nice slide, which finally clarified everything to you. So everything comes at the right time. You just need to be a bit patient. And a full ML horrible training cycle. If you are suffering from insomnia, this is the slide to look at. Instant sleep guaranteed. Downsides, we saw everything, especially adversarial risk at length. And this was the future. So, with that, we come to the conclusion. Go ahead and do whatever we discussed. I hope your love and support for this channel will grow and the channel will do wonderfully well in the coming weeks, months, and years. This was Mentor Sandy bringing you AI for real impact. See you soon. All the best.